called differentials and linear approximation. And the good news is you've done all of this already. It's just new words. So when we're talking about differentials, it's about taking a derivative and finding an approximate change in a value. And then when we talk about linear approximation, that's just the equation of the tangent line. So we've done these things. It's just we're looking at them a little bit differently today. Okay? So that's the good news. So why they make all these different things, but this is all different parts of it. So let's kind of start with differentials. And my notes look a little bit different than probably what Dr. Taylor did on the video, because I wanted to be specific about what was what. On the old notes, they didn't have that, so I changed this up just a little bit. Not a lot, but. All right, so we talked about, not a whole lot, but these deltas, the triangles in calculus, that stands for the change in something. Okay, so in calculus, when we talk about the slope, we say it's the change in y over the change in x, which is just our regular, y2 minus y1, that's the change in y, over x2 minus x1, that's the change in x. So that's just the formula for slope, but that's in calculus, that's what it looks like. All right, then we have the slope of the tangent line, which is dy dx. Okay, so notice it's not delta, we change them to the d's. Okay, so when we do differentials and when we do linear approximation, if you're asked to find an actual value, they're talking about the slope. Okay, so I'm going to write the word actual here. And you'll see those words as we do the problem. So anytime you see actual, we're talking about delta y over delta y. When they ask you for an approximation, then we're looking at the slope of the tangent line, dy dx. So this is an approximate value. Okay. And as we'll see, going through this section, the actual value and the approximate value are pretty close to one another. Okay. So for a lot of things in real life, we don't need an actual value. And to find an actual value, a lot of times, it's hard to do. The problem is hard, whatever the case may be. It's much easier to approximate and give our answer that way, knowing that it's just an approximation, knowing that there's some error in our answer. But it's still, for some applications, that's all you need. As long as you get close to an answer, people are happy with that. Okay? So, we round all the time in real life. So depends on the job. Sometimes you need a specific answer, and sometimes you don't. All right, so we're going to go through and kind of talk about these today. So this is what's not on the notes that if you watch Dr. Taylor's video. But dy dx, that's our definition of derivative. That's a derivative right there, dy dx. The differential is this formula, which is dy. So notice all we do is we take the f prime, which is your derivative, and take the dx over here and just multiply it to this side. Okay, so I have some students that can't get this through their head. So when you find a differential, you know you're taking the derivative and then you stop. So I just want you to remember, if I ask you to find the derivative of a function and then I ask you to find the differential of a function, they are not the same. They're close, but it's not the exact same thing. Okay? All right, so all we're going to do to find a differential, which is going to be our approximation, because these have the dy's and the d's. So these are going to give us our approximate numbers. Okay, we're going to take the derivative and multiply by dx. Okay, so Dr. Taylor did a couple with you. I'm going to do one that's easy and one that's a quotient rule. It doesn't matter what you have. If the problem says find the differential, that's what you're going to do. Okay, so for number 3, we're going to start by taking the derivative. So dy dx, it's the left side. And then the derivative of 5x cubed would be 15x squared. Okay? And you put dx dx, but that's going to cancel out. So we don't need to do dx dx. All right, so that's the derivative. That is not the differential. So if I want to find the differential, which these directions say, I would take the dx from the denominator and multiply it on the right-hand side. That's a differential. So a lot of you would say, well, that's just being picky. No, that's how we find these approximate values that we're getting ready to find. Okay, so derivative, differential. One extra step in that. So if you tell me this is a differential, you get that wrong. That is a derivative. Okay. All right, so number 4, we're going to do the same thing. It's just, depends on the problem. So you might have implicit, you might have different ways to find the differential. Typically, we don't give you guys hard problems to do differential, so that's kind of the nice thing. They stay pretty straightforward. So you wouldn't ever do an application on number 4. Number 4 is just practicing taking a derivative. Okay. So look at number 4. So dy dx. So we're going to do a quotient rule. And we don't even have to clean this up. If you're doing a differential, you don't have to clean it up unless you're going to use it. All right, so we're going to start with the derivative of the top. So that would be 6x plus 4 times the bottom. Leave that one alone. Okay. So the derivative of the top times the bottom minus the top. Leave that one alone. Times the derivative of the bottom. All right, so the derivative of 5 sine of x would be 5 cosine of x. And then the derivative of 2x is 2. All over the bottom square. Okay. All right, so there's your derivative. All right, so your differential will be take this and multiply it over here, right? So if you want to be cheater and cross that out, just put it over there, that's fine. So our differential, I'll just do it real quick, would be all of this times that dx, okay? So I get to use my favorite brackets. All right, so all of this. So, I don't really care that you give me that first step. As long as you remember to stick the dx on the end, I'm okay with not having that first step, but there'll always be a few of you that forget that. So just be careful. All right, so that whole thing times dx. So there's your differential. Okay? And we don't do this a whole lot, so, by test time, which is, we got 5 sections of chapter 3 to do, but so by the end, some of you kind of forget that little piece. So just try to remember that, at least when you're going over the review part, okay? All right, so we good? Okay, so that's a differential. So now we're going to use this stuff. So we just kind of wanted you to see that first. So now let's kind of talk about how there's this difference. Why do we have to care about a differential versus the actual value? Okay, so at the top of the next page, I'm going to write in some things here. Make sure I get all my notes that I wanted to tell you. All right, so up at the top we have that delta x equals dx. Okay, so remember, this is actual, and this is supposed to be approximate. Okay, but notice it says that they are equal. Delta x equals dx. So I want to show you on our picture why that's true. Okay, because then it says delta y, which is actual, is only approximately equal to dy, the approximation. Okay, so let's look at this picture. So I want you to understand, first off, what we're doing. All of this revolves around equations of tangent lines, because finding and solving for a straight line in algebra is way easier than solving for all kinds of curves and functions that we don't know. Everybody can plug in a number to an equation of a line and solve it. So that's what this is all about. All right, so if we look at this problem, this graph, we have a function, the curve. Okay, so this is our actual equation that we're working on. And I want to know what's the change in something from one point to another point. Okay, so here's our starting point. That's what x is, where we're originating. Okay, and we're going to take and find another point. So I'm just using the dotted lines that are on here. And we're going to move to a different point on the graph. Okay, all right. So on this graph, to go from here to here, on the x-axis, do we agree we went from this point on x over to here, right? So we took x and we added the change in x, whatever it was. And so that gives us delta x. That's how much x changed. That's the original graph. Okay, now, look at the tangent line. So here's our point, here's the line, the tangent line for this original point that we started at. So if I look at the x value of change for our tangent line, how much did x change? Well, this value, okay, that's little dx. That's the change in the approximation of x. Well, do you agree that no matter whether we're looking at the original function or the tangent line, that x changes the same amount, right? It doesn't matter if I'm looking at the approximate, the tangent line, or if I'm looking at the real graph. Okay, so once you know dx, you know delta x. If you know delta x, you know dx. They are always the same because they won't change. So x isn't our problem. Our problem is y. All right, so look at your y values. It's over here, delta y. So delta y is how much the original function, the real function, changed. So here's our y value, and here's our new y value. So that's delta y. That's the actual change in y. Okay? Look at your approximate change in y. Here's the original, and here's our new one. So that right there is dy. That's not the same as delta y. So the delta y and the dy are going to be close in value, but they're not going to be the same. Okay? And this is true for any picture, any graph that we look at. That's what's going to happen. Okay? So I just want to spend a minute making sure you understand that, because then this kind of makes more sense. All right, so our delta x and dx, those are good. Always the same. Delta y, dy are different. So how do we find dy? How do we find dy?
Difference between the two, so you'd subtract. Oh, sorry.
Well, if you have a function, though, what we just do earlier,
Derivative times
this is the differential, right? That is the different, dy is differential. So we know how to do this. If I ask you to find the approximate change in y, you're going to take the derivative times dx. That's what we just did, right? So that's why I want to make sure you understand that. So that's why we had to multiply the dx over to the other side. So if you're asked to find an approximate change in y, that's a differential. Okay, so we already have that formula from before. It's f prime of x times dx. And dx, we'll know it's a change in x. We can figure that out. Or it's given to you. All right. Delta y, the actual change in y, we know how to do that. We just take the function values and subtract them. I mean, that's the actual change in y. Okay? So this is that formula, f of x plus a. So I'm going to box this in. So make sure you see that little approximation. So dy was what we just did on the front page. Delta y is an actual change. That's taking function values and subtracting them. Okay? So f of x plus delta x, this is the new amount, new value of x, and this is the original. Okay? So I'm going to write that 2. This is new, this is original. That'll make sense when we get to the problems in a minute. Okay. And then dy, that is a differential. So that's not, if I ask again, so you got to pay attention to what you're asked to find. So sometimes it'll have the symbols, and other times it'll just be words. Okay? All right. So this is not hard. None of this stuff is hard. It's just a lot of new notation. So don't let the notation throw you. Just think about what it is you're doing, and you should be able to get through that. All right, so Dr. Taylor did 5, so let's run through number 6 real quick. Okay. So 6a says we have y equals x cubed. We want to calculate delta y for x equals 2, so that's our starting point, our original number, to x equals 2.01. Okay. All right, so to do delta y, that formula is f of x plus delta x minus f of x. That's just finding the y values. F of, those are y values. All right. So what is the change in x from 2 to 2.01? 0.01. So our delta x would be 0.01. If you have to find that, that's what it is, change in x. All right, so let's see what we got. So we have f of x, okay, so that's 2, plus delta x, 0.01, minus f of x. So we're looking at f of 2.01 minus f of 2. So look at what I said earlier. This is always your new value where you're going, and this is always where you started. So you don't really need to do this middle piece if you see what we just did. We're going to find the y value of our new point minus the y value of the original point. That's how we work that. So this is kind of a crazy looking formula to do something very basic, okay? So it's always the new value where you move to minus the original. Okay, that's important because when that changes in a negative direction, your answer is going to be negative. All right, so we're going to take f of 2.01. Well, that means plug 2.01 into our function. So this is 2.01 cubed minus 2 cubed. So remember, that's just function notation. Plug these numbers into your function. So that's what we're going to do. So 2.01 cubed minus 8. So 0.120601. That's how much y changes in this function exactly. Exact change in y. Okay. All right, now, part B says calculate the differential, the approximate change in y. Okay, well, the differential is the derivative times dx. Okay, that's dy. That's an approximation. All right, so what is the derivative of our function? 3x squared times dx. And this x is always your original. Always you do the original for x in a problem. So we have 3 times 2 squared times 0.01, because remember, dx is the same as delta x. That's always the same. Okay, so that's, once you have one of the x's, you have both. So delta x, dx are the same. All right, well, that gives us 3 times 4 times 0.01, so that's 0.12. And I'm going to put some zeros there, because I want you to look. This is your approximate value change in y. And this was the actual, and they're pretty darn close, okay? And to me, this was a lot quicker. We didn't, going through all this, I don't know that, x cubed is an easy function, so it really doesn't matter. But when we get harder functions, this is going to sometimes be an easier route to take. So we were pretty close in our answers. Okay, so this is from the tangent line, so it's pretty close. This is the original number. Okay? All right, so let's look at another one. Number 7 uses the volume formula. Same thing, though, except I think it asks it in the opposite order. So number 7 says, we're going to look at the volume of a sphere, 4/3 pi r cubed. Use differentials. So as soon as I see that word, that's why that's there. It's an approximate change in volume. So we're going to use the derivative times the change in x to find an approximate change in volume if we go from a radius of 3 feet, so there's our original r, to a radius of 2.8 feet. So we're going to shrink this thing. So we should get a negative answer. So our original r is 3, the new r is 2.8. So what is delta r? So we're not doing x's and y's, we're going to do delta v and delta r, right? Because we got v's and r's in front. So how much did we change from 3 to 2.8? Negative 0.2. We went down. Okay. All right. So use differentials. And it tells you to start by finding dv dr. So just kind of think about, because for some of you this is still kind of crazy with the derivative notation. So typically we use dy dx, okay? But for this problem, think about it, it's always y equals and the x's are over here, right? So that means instead of dy, we're going to be doing dv, and instead of dx, we're doing dr. So our two variables in this problem are v and r, not x and y. So if you ever need to kind of figure out what's what, kind of think about it that way. That helps some of you guys out with the notation, because this is always y over here, okay? All right, so we're going to find the derivative. So dv dr, that's the derivative of v is 1 dv dr. 4/3 pi is a constant, so I'm going to leave that alone. Okay, 4/3 pi is a constant, so all I need to do is take the derivative of r cubed, which is 3r squared, dr, which I don't need, because that's 1. Okay. All right, so we can get rid of the 3's. They're going to cancel out. So dv dr equals 4 pi r squared. That's the derivative. So the differential, dv, is 4 pi r squared times dr. So now I can plug in the radius of 3, the original radius goes in here, and the change in the radius, which was negative 0.2, and I can find this. So 4 pi times 3 squared times negative 0.2. Okay, so we're just plugging those numbers in to our approximate change in volume. Okay, approximate change in volume. All right, so negative 22.6195. All right, so think about the actual volume. If I said, what's the volume of this sphere if the radius is 3? How would you find it? Where would you plug 3? If I needed the volume when the radius was 3. I'd plug it into here, right? I'd plug it into the original function. And then I'd say, all right, what's the volume if the radius is 2.8? And you'd find that, right? Well, what's the difference in volume? You would subtract those two numbers. So that's exactly what the actual values are. So you're just plugging these numbers in to the original function. So delta V, remember we're going to start with our new value, right? So that would be this one. So we're going to find f of 2.8 minus f of 3. We're going to take the y values and find them. And it's always the original guy at the end. So we're going to plug 2.8 into the volume. We're going to plug 3 into the volume. Those are our y values. And subtract those numbers. So f of 2.8 is 4/3 pi 2.8 cubed. So I'm just plugging that into the original function up here. This one. Okay? And then minus f of 3 would be 4/3 pi times 3 cubed. So delta, the deltas are the easy ones. You're just plugging the numbers into the original function. Little d's are the derivative stuff. All right, so just be careful as you compute these in your calculator. It's always easy to make little careless mistakes. All right, so I got negative 21.1450, so make sure that's what you're getting. So look, so our, this one is a little bit off more, but our change in x was more. 0.2 was a little bit bigger than the 0.01. So the bigger the change in x, the farther apart your approximation is going to be to your actual answer, but it's still good. Okay, it's not great, but it's okay. But that's your approximation. This was actual. Okay? All right. So that's all I got to tell you about differentials. So now we're going to move on to linear approximation. This is kind of new, even though it's not really new. This is probably the newest part of this section. The linear approximation is totally equations of tangent line. Just, again, new notation. So try not to get hung up on that. All right, so we okay with differentials? All right, so same kind of picture. We're still looking at a real function versus the tangent line. So let's talk about linearization. Some books, some problems will say find the linearization, and other books, other problems will say find the linear approximation. That means exactly the same thing. Okay? So if I say find a linearization, or if I say find a linear approximation, it's one and the same. Okay? So it depends on how you learned it. Every book, it's a little bit different how it's worded, but they mean the same thing. All right, so it says the linearization of a function f of x at a fixed point A, so you got to have a point to start with, is given by this formula. L of x, stands for the linearization, equals f of a plus f prime of a times x minus a. So I want you to think about that because we've done that. That is exactly what we've been doing since day one. That's the equation of a tangent line. Okay? Doesn't look like it, but it is. So let's kind of go through and show you why that is. Now I'm going to change these numbers around just a little bit with my y's so it's what we've been doing. So instead of y, well, no, because I use y0. All right, I'll just talk you through it instead of changing because I want it to match the graph. All right, so we have a point. Remember, we can find the slope at a point now because we know how to find the derivative. So I don't need 2 points anymore in the slope. So if we have a point, a, f of a, so f of a is your y value, okay? And we want to find the derivative of that, okay? We have our point slope formula. So remember, we did x1 or x2 minus x1, right? No, we did x minus x1. That's what we did. So in our problems from earlier this year, we've been doing y1s and x1s. So that's the only difference. Okay, so we okay with that? We're in college now, we can do that, right? All right, so think about those as the ones. But otherwise, that's what we've been doing, right? Y minus y1 equals m times x minus x1. That was our equation of the tangent line. That's how we always started. And we found m, it was the derivative. So first thing I want you to notice is that the slope is the derivative. So all they did was instead of putting m there, they put f prime of a. That is the slope. And then all they did was take our function value, which is y, f of a, and add it to this side. Okay? So this right here is the same thing as y equals y1 plus the slope times x minus x1. I want you to kind of see what we've been doing. Okay? So we're going to still do what we've been doing, find the equation of a tangent line, and we're going to write it this way. Okay? I don't really care if you write it any other way. You can write it in slope-intercept form. You can write it any way you want to. I'm good with that. It's just that typically when you're doing linearization, this is how you'll see the answers written. Okay, so I want to give you just a quick what that means. Some of you I know don't like the letters and all that. So let's say we started with y minus 5 equals negative 3 x minus 2, right? So we had the ordered pair 2, 5, right? Or 2, 5, and the slope was negative 3. That's what we did, and so all you're going to do is take this number, bring it over to this side. That's what linearization looks like, okay? Whereas we were doing plus 5 over here, and then we'd simplify. So you don't have to do that, okay? So this is what linearization looks like. So it's the same formula. It's just how it looks when you write it out. And then instead of writing y, we're going to change that to L of x. It's the only difference. So nothing from here on out is new, okay? Nothing is new. We're going to find the equation of the line. We're just going to write it a little bit different. Okay? All right. So I just want to make sure you see that because this is the way that your book shows it. This is the way that in WebWorks it'll have the answer. So that's kind of what we're going to use. Okay. So all we have left is to do a few of these linearization problems and approximate some values. So we're doing the same thing. We're approximating values with 1 point. So instead of 2 points, what if you only have 1 point? So Dr. Taylor did numbers 8 and 9 with you. So I'm going to do numbers 10 and 11. All right, so think about what it is when we do any kind of tangent lines. What do we need? We need a point. We need the slope, right? Always. So if I need a point and I need a slope, I have to have a function that I start with. So the easy problems are the ones where they give you the function. So number 10 is what I would consider easier. Number 11, they don't give me a function. I have to come up with a function. And typically it's not going to be a hard function, but that's the difference. All right, so let's look at number 10. Find the linear approximation of f of x equals the cosine of 5x at a equals pi over 2. All right, so first off, in linearization land, a, the point you're starting with, is your x value. Okay, so you got to kind of remember that. So when they give you what a is, that is what x is. So that's the x coordinate of your ordered pair. All right, so remember, we need the point and we need the slope. Okay, to write any equation of the line, those are the two things that we need. We need an ordered pair, we need the slope. So as I've always been doing, we're going to find the the point first. So we're going to plug this number into the original function. That's how you find the y value. All right, so the cosine of 5 times pi over 2 is the cosine of 5 pi over 2. Ooh, this is a good one. Where's 5 pi over 2? Okay, go around the circle one time. All right, so cosine, 5 pi over 2. Get my little scrap paper again. All right, so pi over 2 is up here. Here's pi, 3 pi over 2, 2 pi, right, to go around. All right, so if we're starting at 0, pi over 2, this is 2 pi over 2, 3 pi over 2, 4 pi over 2. So 5 pi over 2 is the same as pi over 2, and it's ordered pair 0, 1. So the cosine is 0, the sine is going to be 1, because we're going to need the sine in a minute. Okay, so 5 pi over 2 is up here. Went around the circle one more time. So the cosine would be 0. All right, so that means our point is, here's your x value, pi over 2. Y value is 0. So there's your ordered pair. So, it's a little tricky plugging things in, but that's what we're doing. So just remember that a is the same as x, and you're plugging that value into the original function to find y. All right, now we need the slope, so we have to plug pi over 2 into the derivative. So let's find the derivative. So f prime. Okay, so chain rule. So derivative of the outer function cosine is negative sine. Leave the inside alone. Times the derivative of the inside, which is 5. So let's clean that up a little bit. So that is negative 5 sine of 5x. All right, so we're going to plug pi over 2 into the derivative and solve that for the slope. Okay, so negative 5 times the sine, 5 times pi over 2. So that's 5 times the sine of 5 pi over 2, which we said was 1. So 5 times 1 is 5. So your slope is 5. Okay. So now we have a slope, we have a point, and now we're going to find the linear approximation. So that's the equation of a tangent line.
Does the negative not go along? Negative.
Did I lose that? I did. Thank you. Thanks. Negative 5. All right. Thank you. All right. So we're going to start with our regular point slope formula. So do that over here. So y minus y1, which was 0. So y minus 0 equals the slope, negative 5 times x minus x1, which is pi over 2. Okay? And then to do linearization, you're going to take this number and just move it over to the right-hand side. So we don't really need to see it, but I'll put it there. So 0 minus 5x minus pi over 2. That's the way that linearization looks. They put the y value in the front. I don't care if you put it in the back. And you don't care, because if you're doing multiple choice, you can probably figure it out. And if it's free response, then you can do it this way. You can multiply it out. You can do it any way you want to. As long as I see the right numbers in there, you're okay. So we would write L of x. And again, the 0 is not important. But so that's what linearization looks like. So it is nothing new. It's the equation of a tangent line. But that's how we're going to get our approximations in a minute.
But because of linearization, we have to keep it 0.
No. I'm just, so if you ever go back and look at this.
Gotcha.
I don't want it like nothing to be here and then the next problem something will be there. So no, you don't have to put the 0 there.
Thank you.
That's just that f of a. That's the y value. That's where it goes. All right, so number 11, we're going to do this same process, but we want to find the approximate value of the square root of 16.1. Now, this is kind of neat. Dr. Taylor did 25.1 with you. This is kind of the whole reason why linearization exists. You think about any radical that you would try to find the answer of, you can't do that in your head. You know, if I ask you to find the square root of 16, I can do that, 4. But if I ask you for the square root of 17 or the square root of 18, I don't know its, its decimal answers. I need a calculator. But if we do linear approximation, which is just using lines, I can plug a number into a line and work it out. So it's kind of cool how this works, that we can actually figure out these numbers that normally we couldn't do without a calculator. All right, so this problem does not give me a function. Okay, so I have to come up with my own function, which usually you can see in the problem. It's the square root of x. Okay, so the first thing, if they're not giving you a function, is you need to determine the function you're going to use. Okay, so our function for this problem would be square root of x. Okay, so I'm trying to find the square root of some value, so my function will be the square root of that value. All right. Now, I need to come up or determine my a value. Okay, remember the ordered pair. I don't want a to be the square root or 16.1 because I don't know that. I want to come up with a number that I can do in my head. So what's a number good close to 16.1 that I know the square root of? 16. All right. So that's my number that I want to start with. So that's x. Remember, a is x. So that's our x value. So that means my point, you gotta have point, you gotta have slope. So if I plug 16 into here, what is y? 4, right? So there's my ordered pair. So unlike this problem where they gave me the function, they gave me a point to start with, I had to come up with my own here. But it's pretty straightforward to know what your function's going to be and what your starting point's going to be. Okay, find something close to what you need. All right, so now the last thing we need then is our derivative, our slope. So we need to do f prime. Okay, so we're going to find the derivative of the square root of x. So that is 1/2 x to the negative 1/2, which is 1 over 2 square root of x, since I'm going to use it. And I'm going to plug 16 into that to find my slope. Okay. Bless you. All right, so we're going to do 1 over 2 square root of 16. That's 1 over 2 times 4, so 1/8. So there's our slope. All right, so here's my stuff I need, always. So let's write the equation for our linearization. So we're going to do y minus 4 equals 1/8 x minus 16. We're going to add the 4 over to the other side. I don't care if it's in front or the back, doesn't matter. Just doing it the way your book does it. So that means the linearization is that formula. I don't really even care if you put L of x, but that's what you're going to see. Okay, so y equals is fine to me. So there's our linearization. Now we can answer the question.
So we only plug in when it says use linearization techniques to approximate?
Mm-hmm.
Okay.
Yeah, otherwise if it just says find the linear approximation, that is the formula. That's the equation. If you're going to use it, then you'll plug in your number. All right, so now we need to find the square root of 16.1. Okay? So look at now this is important for the next one we're going to do in a second. You want to make sure that what you're subbing into your linearization function is what makes your function equal to this. So when I look at this problem, I need to know that the square root of 16.1 has to equal the square root of x, and then I got to solve for x. So in that problem, x will be 16.1. okay? What you plug in here has to be what x equals, not the actual number that you start with. It's not always the same. So keep that in mind when we do number 12 in a minute, and I'll come back to that. But for now, x is 16.1. That's okay. So I'm going to plug in 16.1 here. Okay? For x. So I have 4 plus 1/8 times 0.1. Okay? So 1/8, that's 0.125. So if we do 0.1, so that's 0.0125. So we get 4.0125. All right, so I did need a calculator. I mean, granted, you might need it to do the 0.1 times an 8. But you could do that in your head if you know, and that's not that big a deal. But that is the approximate square root of 16.1. If you actually do the square root of 16.1, okay, so we were pretty darn close to the actual answer, and we didn't have to use that square root function. We used a line. We used the equation of a line to find the answer to a square root function. Okay, so that's kind of neat how that works, and it's pretty close. Usually we get pretty close to those answers. Okay, and so you might be saying, well, why do we need that if we can just do this? But again, remember, these weren't handy a long time ago. Okay, so that's kind of interesting that no matter what kind of crazy function you have, you can use a line to find its answer. So, okay. All right, so let's look at the next one, and this will go into what I just said about x. So this will make hopefully a little more sense. Because I know there's one on WebWorks, like the one we're getting ready to do, and some of you will email me because you're going to plug in the wrong number for this. So let's talk about this. All right, find the linear approximation of f of x equals square root of 4 minus x. So find that first. So that's the L of x equation. At a equals 0, so that's our starting point. So remember, that's x. A is always x. And then use it to approximate the square root of 3.9 and the square root of 4.1. Okay? Now, this is WebWorks, because typically we would not start with x equals 0. What would I usually start with? I want to start with something close to these numbers that I know. So I would start with x equals 4. So if I really wanted to do this close, I would let x equals 4, but I'm going to do what, you can pick any number. That's kind of the neat thing about linear approximation. So we're going to use zeros. That's what the problem says. So if you're coming up with your own, use something close to the number. Otherwise, if you've given something, you got to start with that. Okay, so let's look at our ordered pair. So what's our point? Okay, so we have to do 0 something. So we're going to plug in 0 into here and find the y value. So that is the square root of 4 minus 0, square root of 4, which is 2. So our ordered pair, 0, 2. And now we need the slope, so we're going to do the derivative. So we're always going to start with these things. So what's the derivative? All right, so be careful. This is a chain rule, so you got to watch that -1 on the inside. So the derivative of the square root, it's 1/2. Leave the inside alone to the -1/2. And then times the derivative of the inside, which is -1. And then let's clean that up since we're going to use it. So that's -1 over 2 square root of 4 minus x. So we're going to plug 0 into that to get the slope. All right, so we plug 0 into here. We get square root of 4, which is 2 times 2, so -1/4. So there's your slope. We got our point up here. Now we're going to write our equation, our linear approximation. Okay, so y minus 2 equals -1/4 times x minus 0. Add the 2 over. Now, do you need the 0? Not really. So let's just write this as L of x equals 2 minus 1/4 x, right? We don't need the 0 there. Okay, so that's the linearization. You can leave the minus 0, doesn't matter. WebWorks will take it. All right. So to find the square root of 3.9, let's start with that one. I do not plug in 3.9 into here. If I plug 3.9 into here, I'm going to get the wrong answer. What do I need to plug in and why? So I want to make sure we're clear on that. Okay, remember, this function has to equal this. Remember, our last function was the square root of x, but now that's not our function. So what does x have to be in order for this to be 3.9?
4 minus 3.9?
Not 4 minus what?
0.1.
0.1, right? What's 4 minus 0.1?
3.8.
So that's what you need to plug into here. That's why this is real important. So the very last one we did, the function was square root of x. So we used 16.1 because that is made that equal to that. Okay, so if you're not sure, that's what I always tell you guys to do. Take the function and set it equal to what it is you're looking for. That's what you're doing. And solve this for x. You're plugging in x into the linearization, not necessarily what you need. So if we do that, take square both sides. Okay, move the x over, subtract the 3.9 over, we get x is 0.1. That's going in. Okay, so we're going to do, to find the square root of 3.9, its approximate value, we're going to do 2 minus 1/4 times 0.1. Okay, so that's 2 minus 0.25. 0.025, the 1.75. And if you plug in the square root of 3.9 in your calculator, should be close to that. Oh, that's a 9, not a no. I can't subtract. Right? Okay. All right, sorry about that. 1.975. I thought that was kind of low. All right, now to do the square root of 4.1, think about it. We're going to set square root of 4 minus x equal to 4.1. What's x going to be in this one?
Negative.
Be negative, right? To make that, we got to grow this, so we're going to do a negative 0.1. All right, so we're going to do the same thing, except negative 0.1. So that's going to make that positive. Okay. So those are your approximations. If you do the actual values, they'll be very close to that. Okay. So my only concern with linearization is that you're plugging in the right number into the formula. That's kind of the key to that one. All right, so number 13 is another WebWorks problem. This one's nicer because it gives you the function. Tells you your function is x to the 6th, and they give you your starting point of a is 2. So this is easier, I think. And we're going to use our linearization to find, so this is good. What is 2.001 to the 6th power? Who the heck can do that in their head? Okay, I know what 2 to the 6th power is, and that's what I'm going to do to help me approximate. But without a calculator, that's not so easy to do. So this is kind of cool how this works. I think it's cool, but, you know, we're using our brains a little bit to figure this out. All right, so we're going to start with our function. We have that, x to the 6th. We have our x value, which is 2. So we need our ordered pair. Okay, so put 2 in the original function, raise it to the 6th power. So 2 to the 6th power is 64. So there's our ordered pair. Then we're going to find the derivative. That's easy enough, 6x to the 5th. We're going to plug 2 in there to find the slope. So f prime of 2, 6 times 2 to the 5th, so that's 6 times 32. What is that? 192. So there's your slope, this humongously big slope. That's why I know this is web work. All right, so we have a point, we have a slope. So we're going to do y minus y1 equals m times x minus x1. Find our linearization, add the 64 over. All right, so there's our linearization. Okay. All right, now, what do I need to plug in for x to find 2.001 to the 6th power? So am I actually going to use 2.001? This one I am, right? Because x to the 6th has to equal this. So in order for it to equal that, x has to be 2.001. So I'm going to be subbing in 2.001. Into here. So I have 64 plus 192 times 0.001. Well, again, you almost don't need calculators for this because usually you're doing tenths and things like that. So this is just going to be 64 plus point, what? How many places are you going to move the decimal? 3, so that's 0.192. So we get 64.192. Okay. And that took us not much time. I didn't even need a calculator for that. But if I took 2.001 and raised it to the 6th power, I got 64.19224. So you can't get much closer than that. Okay. And we did need the calculator to do that. So these approximations, again, cool. Okay. They're cool. Don't forget that. All right. So those are kind of the harder problems. Now this last problem, number 14, I don't ask you anything about relative error, percent error. We don't do that on your final exam. The only reason number 14 is on here because there's one problem on WebWorks. So this way you'll have what to do. It's very easy, but there's some formulas involved. You do not need to know those, okay? So I wrote them on your paper so you'd have them. All right, so this one doesn't take too long, so let's look at number 14. All right, we have the edge of a cube that was found to be 60 centimeters. That's the edge, so each side of the cube, with a possible error of 0.5 centimeters. That's the change. That's delta or the dx, okay? Use differentials to estimate the maximum possible error in volume. Okay, so let's talk about what we have and what we're doing. So volume using a cube, you guys remember the formula? So that's side times side times side, right? So S cubed is the volume. When you have a cube, all the sides are the same. Length times width times height. All right, so we're going to be doing dV ds instead of dy dx. So dV ds. Okay, so if the volume is the side cubed, and we're doing a differential, we need the derivative. So dV ds equals 3s squared. So the differential, 3s squared times ds, okay? So this is the approximate change in volume. This is not exact, this is approximate, which is what they wanted us to do, estimate. So what are we going to use for our side? We started with 60, and what's the change? The change is your error, how much it's off by, right? So there's your change. So we're going to do 3 times 60 squared times 0.5. All right. So that's the, now think about that. That's a cubic centimeters, you know, I mean a centimeter is not a big thing. But if your side went from 60 to 60.5, that's only a change in the side of 0.5. The volume changes by 5,400 cubic centimeters. That's a huge change for just changing the radius or that side that much. All right, so relative error, okay? Find the relative error in volume. So here's the formula. for relative error, so we are not using y's. So our relative relative error would be dv over v, right? We're using volume instead of y's. All right, well, we already found dv, that was 5,400. What is v? What does v stand for? The volume, right? So where are we going to find v? We're going to plug 60 into here. So v is 60 cubed. So that is 216, 1, 2, 3. No. Nope. So 5,400, we're cubing it. So 216,000, and then that is 0.025. All right, that's the relative error. Again, you won't have to know this for the test. This is just to get you through WebWorks. But that's how you do it. So it's pretty easy, but still, it's a formula. All right, and then part C says find the percentage error. So that's just to take what you found and write it as a percent. So you multiply it by 100. So we would take 0.025 times 100. So that's 2.5. So that's, again, for WebWorks. I will not ask you that on the test. Okay, but just so you have it to do that problem. All right, so we can stop recording, Sean. Thank you.